Today we are going to be working through an example of calculating the electric field of a point charge. Let's set up the problem. We have a point charge, let's call it Q, and we know that the electric field of a point charge moves out radially in all directions from the charge, like so. By drawing the diagram in this way, we recognize that the point charge has a symmetry in how the electric field moves away from it. We will choose a Gaussian surface, a spherical Gaussian surface around the electric field in this way to exploit this symmetry. By drawing the diagram in this way, we notice that the electric field will have the same magnitude at all points on the sphere, and this will allow us to exploit the symmetry in such a way that we can easily calculate the electric field using what's called Gauss's law. Now, Gauss's law has the integral form of the closed surface integral of the electric field dotted with the infinitesimal area vector, and this is equal to 1 over epsilon naught, which is the permittivity of free space, multiplied by the charge enclosed by this Gaussian sphere, in this case, Q. Now that we've set up the problem, let's work through some algebra. So we're going to start with the left-hand side of the equation, where we have the electric field dotted with the infinitesimal area vector. Now, to begin with, the infinitesimal area vector for the surface of a sphere will point perpendicular to the surface at all points around the surface. In other words, radially at all points around the surface. Now we remember that the electric field, E, is also radial at all points around this Gaussian surface. This is going to be a massive simplification for us in this side of the problem, because the dot product of two vectors that are parallel at all points is simply the magnitude of these two vectors multiplied together. This means that this equation will become the closed surface integral of simply the magnitude, we can write it in this way, the magnitude of the electric field times the infinitesimal area, no longer a vector, and that is still equal to 1 over epsilon naught times the charge enclosed. And now that we have the magnitude of the electric field, we can use one more simplification, in that at all points around this Gaussian surface, the electric field has the same magnitude. This means that we can pull it out of the integral because it will be constant. And we can further simplify this equation. In this way. Now we're going to take it one more step further and know that the closed surface integral of a sphere is simply (4 pi r squared), the surface area of the sphere. And moving forward, we have one more simplification to do before we finish the problem. So what we've come to so far is that the magnitude of the electric field times 4 pi r squared, which is the closed surface integral of the infinitesimal area vector, is equal to 1 over epsilon naught times the enclosed charge. And our last simplification is that recognizing that the enclosed charge by this Gaussian surface is simply our charge Q, because the Gaussian surface fully encompasses this charge. So we write it like this, and we can work through our last step. And now we simply have to solve for the electric field. And we remember that the electric field is radial in all directions, so we can go from the magnitude back to the vector simply by remembering that one idea. And here we end up with the electric field of a point charge. And some cool points to notice about this electric field is that it's fully dependent on the charge enclosed by the Gaussian surface, which is just Q, multiplied by this constant out in front, and that the electric field will fall off as 1 over r squared. So we have a 1 over r squared dependence of the electric field propagating radially outwards, which is encompassed in this direction vector here.